Hi, my dear students. Today we will learn about polar molecules. In our previous classes, we learned about electric fields in matter in introduction. Okay, there we see that neutral atoms are neutral. That means there is no built-in dipole moment in atoms. But if we apply electric field, there is a induced dipole moment. There is an induced dipole moment in an atom. Okay, now we learned about molecular polarizability, and there we see that this polarizability tensor, polarizability is a tensor. Okay, all those things we learned in our previous class. Now in this section we discuss about polar molecules. Okay, so polar molecules. We already learned that atoms are neutral. Atoms are neutral if there is no applied field. Okay, applied electric field. Atoms are neutral if there is no applied electric field. At the same time, if we apply electric field, there is an induced dipole moment in an atom. Okay, when electric field is applied, the dipole moment is induced in the atom. Okay, the dipole moment is induced in the atom. Okay, induced in the atom. These two things we learned in our previous class. Okay, now in the case of molecules, there may be built-in dipole moment. Okay, that means you know that molecules are formed using two or more atoms. Okay, if there are two or more atoms, then only we can build a molecule. So in that case, in the case of molecules, there may be built-in dipole moment. Okay, for example, in the case of water molecule, there is a built-in dipole moment. Okay, so molecules which have built-in dipole moment is called polar molecules. Okay, so we already learned that atoms are neutral if there is no electric field. Molecules are made up of atoms, but there may be built-in dipole moment in the case of molecules. If there is built-in dipole moment, the molecules are called polar molecules. Okay, so this is the important point. Molecules are made up of atoms. Okay, there may be built-in dipole moment. Okay, built-in, that means without applying electric field there is a dipole moment. Okay, there may be built-in dipole moments in molecules. molecules. Such molecules are called polar molecules. Okay, such molecules are called polar molecules. Polar molecules. Okay, polar molecules. Example, water molecule, H2O. An example for a polar molecule is H2O. Okay. Now, we can learn more about this water molecule. Okay. We consider this H2O water molecule as an example for this polar molecule. Okay. So as you know, here there is one oxygen atom. Symbolically we can represent it a bit larger one. This is its center, and some hydrogen atom here like this. Okay. This is hydrogen atom. And in this side, here is also one hydrogen atom here. This is the center of the hydrogen atoms. Okay. These two are hydrogen atoms. H plus. Okay. H plus. Here is also H plus. And this one is oxygen atom. Okay. O minus. Okay. Oxygen atom. Now, you can see that here this is the center joining these atoms. Here there are three atoms, two hydrogen atoms and one oxygen atom, and there is 105-degree bending. Okay, 105-degree bending between these atoms. Okay, so the hydrogen atoms and oxygen atom forms a structure like this. There is an angle 105-degree between these hydrogen atoms. Okay, and so due to this particular structure, there is a net negative charge at this point, at this oxygen atom, and a net positive charge opposite to this point. Okay, as you know, you can see that here there is a dipole moment here, there is another dipole moment here. The net resultant dipole moment points like this. Okay, so net negative charge here and a positive charge opposite to this one. Okay, so there is a built-in dipole moment in this water molecule. Okay, so here one node, okay, bent 105-degree. Due to this bending, there is a net dipole moment. Okay, built-in dipole moment. Built-in dipole moment in water molecule. Okay, built-in dipole moment in water molecule. And the negative charge, a net negative charge at the vertex okay, vertex means here nearest to this oxygen at the vertex, and net positive charge opposite to this, opposite to this point. Okay, That means here you can see that dipole moment points from negative to positive. Okay. So here there is a dipole moment like this. And I think I can draw this here. Okay. So a dipole moment like this. This is minus, this is plus. Okay. And the other dipole moment like this. This is plus, this is minus. So the net dipole moment is along this direction. Okay. Net dipole moment. If you split these dipole moments, you can see that this horizontal components cancels out and there is a net dipole moment along this direction. Okay. This is the vertex, which is the position of oxygen atom, and opposite to this one, here there is a positive charge. So resultant dipole moment, okay, this is the resultant one. The resultant dipole moment, which is shown here in this, like this. Resultant dipole moment points like this. Okay, net negative charge at the vertex and a positive charge opposite to this negative. Okay, this is about this water molecule. Due to this built-in dipole moment, the amount of the dipole moment is 6.1 into 10 raised to minus 30 coulomb meter. This is the dipole moment. For water molecule, this is the dipole moment. Okay, 6.1 into 10 raised to minus 30 coulomb meter. Okay, this is coulomb meter. Due to this built-in dipole moment, this water molecule is a very good solvent. Okay, water molecule is a very good solvent. Good solvent. This nature is due to the built-in dipole moment of the water molecule. Okay, so molecules can be polar or non-polar. If the molecule is neutral and if you apply an electric field, there may be induced a dipole moment. In that case, the molecule is called non-polar molecule because there is no built-in dipole moment. Dipole moment is induced only after applying an electric field. Okay, then the molecule is called non-polar molecule. If there is a built-in dipole moment without applied field, then the molecule is called polar molecule. Okay, water molecule is a polar molecule because due to its particular structure, it has a built-in dipole moment. Okay, so this is the difference between a polar molecule and a non-polar molecule. Non-polar molecules. In this case, there is no built-in dipole moment in a molecule. But when we apply electric field, there is induced dipole moment. Okay, there is induced dipole moment. Okay, these molecules are called non-polar molecules. Okay, these molecules are called non-polar molecules. Okay, non-polar molecules. Okay, so if the molecule is polar or non-polar, if there is polarization somehow, we have to discuss about it. Okay, there are two types of mechanisms to induce polarization, to develop polarization. Either it may be built in the molecule, then the molecule is called polar molecule. In the case of non-polar molecule, if we apply electric field, there is a induced dipole moment. Okay, these are the two two mechanisms where materials exhibit polarization or dipole moment. Okay, now we can move on to the theory of this alignment of dipole moment. Okay, alignment of dipole moment. Alignment of dipole. Okay, now suppose that the dipole moment is oriented like this. Okay, this is the dipole moment. This is the minus charge and this is the plus charge. Okay, the dipole moment in the molecule is aligned like this. Consider a dipole. Okay, consider a dipole of length d. Okay, of length d and origin of the coordinate system is fixed at midpoint of the dipole. Okay, fixed at midpoint of the dipole. For the analysis, we assume a dipole like this. This dipole has length d and we assume the origin of the coordinate system at the midpoint of this dipole. Okay. Now, suppose that we applied some electric field. Okay. Let it be uniform. Okay. That's case 1. Okay. I think I can do it in 2 steps. The first one is the case of electric field. Okay. Electric field. The case of electric field. Let uniform electric field. Okay. Uniform electric field. Then what happens? If we apply electric field along this direction, this is the electric field, then what happens? Then force acting on this along this direction, this is F plus, this F plus represents force on positive charge Q. Okay, this is given by QE. At the same time, here force acting on this negative charge is represented by F minus. Okay, and this F minus is given by minus QE. Okay. If we apply electric field like this, there is force acting on these two charges. On positive charge, force is acting along this direction, F plus, which is given by Q into E, and on negative charge, force is acting along this direction and it is given by minus QE. Okay, this here showing the electric field. Okay, force is acting. Force on this charge is along this direction. This is F minus. Okay, F minus. This is equal to QE minus QE. Okay, minus Q. F minus equal to minus QE. F minus represents force on negative charge. Okay, it is given by minus QE, and force on positive charge is given by F plus. Okay, now what happens to the system? If we apply uniform electric field, you can see that the net force on the charges cancels out because plus QE balanced by minus QE. Okay, so in this case, net force on dipole is 0. Okay, because you can see that net force is given by force on positive charge plus force on negative charge. Okay, this is given by QE plus minus QE, and this is equal to 0. Okay, so force on the dipole, net force on the dipole is 0 in the case of uniform electric field. Okay, but there is a torque acting on the dipole. You can see that here two equal and opposite forces but acting on different points in a line. Okay, so there is a torque acting on this dipole. Okay, torque acting on the dipole. Okay, this torque try to rotate the dipole. Okay, so torque acting on the dipole, which is represented by capital N. Okay, this N is equal to, you can write here, R plus cross F plus. This torque is measured with respect to the midpoint of the dipole. Okay, the torque acting on the dipole with respect to the midpoint of the dipole is given by R plus cross F plus R minus cross F minus. Okay, and you can see here that we are measuring this torque with respect to this point, this midpoint. So R plus represents this distance. This is plus d by 2. Okay, R plus is represented by plus d by 2. So you can write here d by 2 cross F plus is given by QE. Okay, QE plus R minus represent this distance. We assume that this is the origin. So we measure from here to here. So this distance is given by minus d by 2. Okay, minus d by 2 cross minus QE. Okay, so you get here Q D cross E. Okay, Q D cross E equals, QD represents dipole moment P. So you can write this as P cross E. Okay, so torque acting on a dipole in a uniform electric field with respect to the midpoint of the dipole is given by torque equal to P cross E. Okay, but in this case, in the case of uniform field, there is no net force on the dipole, but there is a torque. This torque is given by this expression. Okay, now we can extend this study to non-uniform field. Let non-uniform electric field okay. Now what happens? Now you can see that there is a net force because this time electric field is not equal. Non-uniform electric field. Okay. So net force on the dipole is given by F plus F minus. Okay. Now you can write this as Q into E. This time I can write this electric field as E plus. E plus represent electric field at plus Q. Okay. E plus represent electric field at plus Q. Then minus Q into E minus. Okay. This represents electric field at minus Q. Okay. E minus represent electric field at minus Q. E plus represent electric field at plus Q. Okay. So now what happens? Now you can write this as Q into E plus minus E minus. Okay. Or we can write as the net force on the dipole is given by charge Q into change in electric field. Okay. Difference between the electric field. Difference between the electric field that charges plus Q and minus Q. Okay. So you can write this as Q into delta E. Okay. This delta E represents difference in electric field at plus Q and minus Q. Okay. This is the net force acting on this dipole if the field is non-uniform. Okay. Now we want to find out what is this difference in electric field, delta E. For that, we can see that the electric field is a vector, right? Because here also you can see that E plus have X, Y and Z components. Similarly for E minus X, Y, Z components. Okay. So here this variation delta E can be represented as using three components. That means suppose this delta E is a vector. We already written like this. So you can write this as delta EX X cap plus delta EY Y cap plus delta EZ Z cap. Right? Because delta E is the difference between the electric fields at plus Q and minus Q. Okay. So difference between X components, difference between Y components and difference between Z components. Okay. Now we can assume that this dipole has its length, the day is small. Okay. Usually small dipoles. Let dipole is small. Okay. Dipole is small. Okay. Then you can approximate this delta Ex by gradient of electric field, okay, gradient of electric field component along the direction of the dipole, okay. Gradient Ex along the direction of the dipoles gives you this change in X. Similarly for Ey and Ez. So you can write this delta Ey as gradient Ey dot D. Similarly, delta Ez by gradient Ez dot D. Okay. Now, using these approximations, we can write this difference in electric field. Okay. You can substitute for this delta Ex, delta Ey and delta Ez from here. Okay. Then what you get? Delta E. You can write this delta E as D dot gradient E. Because you can substitute this here and this here. Okay, then you can write it in a beautiful form like this. You know that this is dot product and this is commutative. You can write this as D dot gradient Ez. Okay, then using this directions X cap, you can write this like this, vector E. Right? Okay, or if you need more clarification, you can write here Ex, X cap plus Ey, Y cap plus Ez, Z cap. Okay, so you can write here D dot gradient E. Okay, this is the net difference in electric field. Okay, so the net force F, you can write this net force F as Q into D dot gradient E, or Q, taking Q inside, you can write this as dipole moment P dot gradient times electric field. Okay, this is the net force acting on a dipole if the field is non-uniform. The electric field is non-uniform. Okay. In this case also, you can see that the torque acting on the dipole is given by the same expression N equal to P cross E. We already done in the case of uniform electric field. Okay. So torque acting on the body is given by the same expression if it is evaluating with respect to the midpoint of the dipole. Okay. If it is not about the midpoint, there is an additional term like R cross F. Okay. There you have to use the rules for evaluating the torque with respect to some other axis. Okay. So this is about the force on a dipole if we apply electric field. Okay. N is given by P cross E. If it is with respect to the midpoint, okay, torque with respect to midpoint, otherwise torque equal to P cross E plus R cross F. Okay. So, what we get from this analysis, we can see that if you apply uniform field or non-uniform field, there is a torque acting on this dipole. Okay, this torque try to align the dipole along the direction of the applied field. Okay, so if we apply electric field, the dipole moments in the molecule, the polar molecule, align in the direction of the applied field. Okay, if there is no built-in dipole moments, still the applied field try to align the induced dipoles along the direction of the applied field. Okay, so due to the applied field, there is a torque acting on the dipoles. Whether it is induced or not, always there is a torque acting on this dipole. This torque try to align them along the direction of the applied field. Okay. So we will discuss about polarization. Okay, so we see that the applied field try to align the dipoles along the direction of the applied fields. Okay, so in the materials we use the parameter polarization to represent the amount of measure of dipole moment. Okay, it is a measure of how much a material gets polarized. Okay, this polarization is represented by capital P. Okay, capital P. It is given by dipole moment per volume. Okay, dipole moments per unit volume. This can be dipole moments can be either it can be induced or built-in. Anyway, the amount of dipole moments per unit volume gives us the polarization. Okay, so this is all about the nature of materials in electric field. Okay, so in these sessions we learned that materials can be classified as polar or non-polar. If there is built-in dipole moments, we can call it as polar molecules and polar materials. If there is no built-in dipole moments, but there induced dipole moment if you apply electric field, those materials are called non-polar materials. Okay, so if we apply electric field, these dipole moments try to align along the direction of the field. This is called, the measure of this dipole moments per unit volume is called polarization. Okay, so polarization gives us how much a material is affected by electric field. Okay, so I think I can wind up now. In this session, we learned about polar molecules, non-polar molecules, and the alignment of dipole moments. Then we extend this to polarization. Okay, so learn well. Thank you.